I was actually just looking at, just on the other reports to get saw.
So essentially, Pollux finance report in the appendix in the polarimeter.
Awesome.
And a couple of names that we like.
Okay, so yes, resend it when you can.
Mm-hmm. Yeah,
awesome. Thank you.
As soon as possible. If it doesn't work, I will send it my Gmail.
Okay, so we've got 30 minutes. I'll give you like a 5-minute line.
30 minutes?
You could talk slower than you.
No. Yeah. Lots of things to say. And well,
yeah, I'll give you
my English is so anyway, so nothing compared to some of the guys I saw today.
But a much better accent.
Well, I wish. I wish it would.
Waiting on
The particular?
All
right.
I'll give you. I'll make you.
What's going on? Well, too many of them. Your laptop is not big enough. You need a bigger laptop. It's too flashing around.
Okay, let's start the last session of the day. My name's Chris Packham. I'm from University of Texas San Antonio. Let's start off hearing about massive stars in the local universe and far beyond by Jean-Claude Bourret from LAM. Thank you.
Thank you. So, good afternoon, everyone. And so, first of all, a big thank to the organizers for inviting me to give this talk on the properties and evolution of massive stars and what HWO could do for us. For those who care about massive stars. But for those of you who might not care at first on these stars, I prepared a slide to explain why we should care about massive stars. So massive stars are those born with masses higher than 8 solar masses typically. And because of this very fundamental property, they are rare, they live fast and die young in spectacular explosions, the core collapse supernovae. Through a large fraction of their life, they have very high temperature, typically above 20,000 K and up to 200,000 K in some stages. And because of that, they have very strong UV ionizing flux. This same ionizing flux is pushing a dense and supersonic wind, which transfers lots of kinetic energy to the ISM. And so the winds, together with the ionizing flux, play together to create ionized bubbles and large H2 regions. So massive stars are also responsible for the nucleosynthesis of elements beyond oxygen and all the way up to the iron peak. And these elements are transferred into the ISM through the stellar winds and when the stars explode, as I said, as core collapse supernovae. So through all these properties, so very high luminosity, strong winds, strong ionizing flux, important nucleosynthesis, they drive the energy budget of the galaxies, and they drive the full momentum and chemical evolution of the host galaxies. So massive stars, either single or binaries, will evolve to the point of a collapse. They form eventually a degenerate core. This degenerate core will collapse into a compact object, either a black hole or binary. And these black holes or binary are, or black holes or neutron stars, sorry, are the progenitors themselves of gravitational waves events. Finally, I think it's important to say that it's likely that massive stars have played a role in the reionization of the universe and in galaxy assembly. So for all these reasons, I think we can say that we should care about massive stars. So like every other type of star, the evolution of massive stars is first determined by their mass. But apart from mass, there are some important drivers for the evolution, which are rotation, mass loss, metallicity, the presence of a magnetic field, and something that I won't discuss in this talk because I don't have time, it's binarity. Binarity is really super important because up to 70% of massive stars live into binary systems. So I will start with by discussing some of the effects of these mechanisms, and I will start with rotation. So the first effect of rotation is to somehow flatten the star, with the polar radius being smaller than the equatorial radius, and this induces non-uniform temperature, effective, and gravity on the surface. Rotation also produces transport of angular momentum and chemical rotational mixing. And so what you can see in this HR diagram is that rotating stars end up their lives here. The points that are indicated here as are the end point of the life of the star for rotational for models with rotation and without rotation. And so you can see that they end their lives in different positions. One important effect of rotation also is to extend the duration of the main sequence of massive stars, and this is simply because of the mixing. There is some hydrogen that is taken from above the central core. And this hydrogen is brought directly to the burning core, and so there is an extension of the duration of the main sequence. One important point too is that the location of a star in the HR diagram now, as you can see, depends not only on mass, okay, but also on rotation. For different values of the rotation, you could have a star here. And you could think that it has a different mass. So coming back to the effect of rotation on rotational, what we call rotational mixing, this has an impact on the chemical abundance profile in a star, and this is something that we measure at the surface of the star. So, for instance, here it's illustrated on the case of nitrogen. As you can see, models over time predict different chemical enrichment of nitrogen for different values of the velocity, and so the enrichment is stronger for higher velocity. This is simply because one of the mechanisms that is responsible for the fluid movements inside the star, which will bring the freshly nucleosynthesized nitrogen from the core to the surface, is operating at higher velocity. Okay, so what about mass loss? So on this plot, there's the evolution of a 20 solar mass star for which it's an experiment, numerical experiment. The mass loss prescription has been reduced by a factor of 3 and by a factor of 10. And what you see is that reducing m dot by a factor of 10 on the main sequence has almost no effect. And the strong effects start to show up only at the end of the life of the star. But at this stage, the value of the mass loss is up to 35 times the value of on the main sequence, and not on the main sequence. Well, obviously, these effects get stronger when the mass gets higher, because simply the mass loss rate scales up. And integrated over the full life of a star, up to 70% of the initial mass is lost through stellar winds. These are models computed for solar metallicity. So the thing is, one thing that needs to be remembered is that there are large uncertainties on the intrinsic absolute values of the mass loss rates, and this is from the main sequence all the way to the very last stages of the evolution. And this is illustrated here for where you see the relation between the initial mass and the ratio of final to initial mass for different prescriptions of different algorithms used to compute models. You see there is a large variety of ratio obtained at the end of the life of the star. So what about metallicity now? So metallicity, when you go down in metallicity, it means lower opacity, and lower opacity means that the star is going to be more luminous, but it's going to be also more compact, because there is less pressure inside the star. And a star that is more luminous and more compact is hotter. So basically, the decrease in metallicity corresponds to shifting the ZAMs blueward to hotter temperatures. Because the stars are also more compact, we expect that the effect of rotational mixing are stronger at lower metallicity. And this is illustrated here, where you see that going down in metallicity from the galaxy to LMC and SMC, you have stronger gradients of enrichment in nitrogen for I think there are 2 masses, 40 and 15 masses. Okay, the other impact of metallicity is on the wind, because the winds of massive stars are radiatively driven. So this is illustrated here on some observations of different massive stars, O stars, in the SMC in blue and in the Milky Way in red. And you see that the P Cygni profiles, which corresponds to the wind, are stronger in the Milky Way than in the SMC. Okay, so don't pay attention to the details of this relation, but basically it's the wind momentum of the star, and you can relate it to the luminosity. And observational programs have shown that there is a strong correlation between the luminosity, and I've confirmed that it's a strong correlation, and you can derive that the mass loss rate is depending on the metallicity with this exponent, and this has been confirmed by theory. So there is a good agreement, although to be fair, this part is poorly constrained, because these relations have been established on optical data. And in this regime, the H alpha line is really poorly sensitive to the wind. So when implemented in stellar evolution models, the different algorithm for mass loss scale with metallicity, and then you see that the final to initial mass relation gets closer to the one-to-one relation. And just that's because the wind gets weaker. Overall, this yields in the end that the supernova precursors gets more massive at lower metallicity. And again, this is due to the mass loss reduction. But so the realization that gravitational wave progenitors, black holes, have masses higher than typically 25 to 30 solar masses points to an origin of that is massive stars evolving at low metallicity and losing very little mass. And yeah, again, this is typical of very low metallicity environments. Okay, I'm gonna stop through talking about this, and I will say a little bit more about how we get information about what I just presented. So we obtained it mostly through spectroscopy, and there are two preferential ways to do it for massive stars. It's UV, where we get the most information. As you see, we have plenty of diagnostics to derive, to infer the value of the mass loss rate, the presence of shocks, the terminal velocity of the wind, but also, and very importantly, there are iron forest lines, which is providing us the only tool we have to measure the iron abundance in the star. Iron is important because it's the principal driver of the winds of the stars. Then we can do it in the optical too, and with the optical we can mostly access to the helium and hydrogen lines, and then get a grasp on the TF and log G values for a star. So in this context, I want to acknowledge the contribution of two large programs, Ulysses and X-Shooter. So Ulysses is a large program, it's a legacy program, sorry, on HST in the UV, and X-Shooter is the counterpart of Ulysses on X-Shooter at ESO. So these programs allow us to improve our knowledge of the physics of massive star with the so they are performed for LMC and SMC stars, and so at this point the SMC represents the last point, the lowest point in metallicity that we have been exploring so far. Well, there are a few stars in lower metallicities galaxies, but just a handful. I will now address some open questions that could be addressed by a program performed on HWO. And I will start with one point that I didn't address yet, which is about the formation of massive stars and the IMF. One thing that could be tested with HWO is whether the IMF is universal. Where can we test this assumption? And what is the upper stellar mass limit? Here I show you a blow up of the region R136 in the Tarantula Nebula, where each of these stars here has a mass of 100, 150 solar masses typically. And then we can also address the question of whether the stellar IMF is the same in galaxies, starburst galaxies, than in the Milky Way. Now, and so as I said, uncertainties on the mass loss rates are many. So I will go quickly through two problems that we are facing right now on the physics of stellar winds. One is clumping. So we showed a while ago that you need to reduce the mass loss rate by a factor of 3 to 10, typically, to get an agreement between models and observations. If you use the mass loss rate derived from optical data. The other important problem for the theory is called the weak wind problem, and this is illustrated here. So in red, you have the PCV profile computed for the mass loss rate that is expected by the theory, and you see it is way too strong. And in blue is the best fit model. So if you do that for several stars, then you can get this kind of relation, and you see a breakup in the relation at luminosity 5.2, which is totally not understood. I just want to mention that very recently we got a program accepted on JWST to test, to study in more details this problem using infrared data. In the infrared, there are a couple of lines that are really way more sensitive to the mass loss than even UV, turns out, in the very weak winds regime. What we don't know is, so as I said, we don't know about clumping and weak winds, but we don't even know, and it's worse, what kind of outflow massive, really metal poor massive star experience. So I show you here a status of 3 spectra in SMC and section A and IC 1613 are galaxies with metallicity supposedly a little bit lower than the SMC. Those were taken a while ago by Miriam Garcia. So a study based on optical data suggested that the winds of stars in these galaxies were stronger than expected. They were more typical of LMC metallicity. And it turned out that taking some UV spectra of these stars, we were able to model them. And so here in red, what you see is the model for the star predicted. So it's the wind profiles predicted from the M dot measured from H alpha, and you see that it's way too strong. So when you use the UV data, then you can reduce the mass loss all the way down here, and which is more in agreement with the intrinsic metallicity of the galaxy. So this is to underline that UV is super important to measure accurately mass loss rates. More generally, we don't know a lot about the evolution of massive stars in low metallicity environment. We don't know, for instance, how the fundamental parameters are going to evolve with metallicity. And for instance, one important case that we could address with UV and HWO is what we call chemical homogeneous evolution. So it is predicted that massive stars undergoing lots of angular momentum in the core have a strong mixing from the central core to the surface, and this is occurring on very short time scale, to the point that the star is completely mixed to a homogeneous composition. And a star going through chemically homogeneous evolution is never evolving to the cool side of the diagram. It evolves directly to the hot side of the HR diagram. And seems that this constraining this evolution is really super important, because some of the scenario for explaining the gamma rebirth, like the collapse star, need to have stars evolving into a chemically evolution, homogeneous evolution. Okay, so to address that, we need to go down in metallicity. And here is the present status with so the LMC and SMC here. So these are the galaxies that are being covered right now with Ulysses. And you see here the log over H of these galaxies. The thing is, we need to really measure iron rather than oxygen for these galaxies to be able to understand what's going on in the winds of the star. And this is nicely summarized here by a figure created by my colleague Miriam Garcia in Madrid, which she calls the roadmap to the early universe. And each of these galaxies in this plot provides a ladder in low metallicities, and by addressing the physics of the stars in these galaxies, then we can infer what's going on for the first generation of stars. Okay, so the limit in observationally stands here. So you have like a collection of spectra taken for IC 1630, which is here. Distance modulus 23 or something. The thing is that to get each of these spectrum takes like 5 orbits of HST with COS, and it's low resolution. So if you want to do a systematic program with high resolution, which you need to characterize precisely the parameters of the star, it's impossible to do it with HST. Okay, I'm going to skip this, but just to show that what is the Kahn's limit in optical. So the goals, as I said, are to go down in metallicity, and we are fortunate that in a reasonable volume of the universe around us, there are many galaxies that would provide this ladder in metallicity that we can use to perform the program. With ultimately a goal which is to reach UV spectra in IZ in Zwicky 118. Okay, so this all the science goals translate into these requirements. A spatial resolution of this order, which is there to be able to separate stellar populations in galaxies at 2 megaparsec, and to resolve a region like R136 up to IC 1613. Then we need large collecting power so that we can go down in go away or beat the absorption. We need at least a medium resolution with possibly multi-object optical and near-infrared spectroscopy, and UV spectroscopy with multi-object mode. Okay, so one of the existing instrument that could help us for that, at least for the optical side, is MOSAIC, where the resolved stellar population beyond the local group is one of the 4 major objectives of this instrument. But even with MOSAIC, even with the adaptive optic on MOSAIC, an instrument like that will struggle to at least in the optical blue region, to disentangle the regions that we need to address. Okay, I'm going to skip this one then. Just one thing. As I said, magnetic fields have a stronger influence on the evolution, and I would like to advocate that one important capability for LIVOIR would be to have spectropolarimetry in the visible and in the optical, in linear and circular, and then we can address plenty of of physics for the evolution of massive stars, but for other objects. Okay. And I will leave you with the summary.
Thank you very much. We've got time for 2 quick questions. Anything online? All right, going once.
Twice.
Going twice. All right, you explained it too well. Let's thank our speaker again. Thank you. Okay, our next speaker is Julia Roman-Duval from Space Telescope, who's going to be telling us about understanding the cosmic buildup of dust and metals with HWO UV spectroscopy.
All right, sound check. Good. All right, thanks. I guess I have to move to, I don't want to break anything. Do you know where the presentations are? Got it. All right, perfect. Okay, right, all right. So we've heard about the Baryon cycle, we've heard about galaxies, and I'm here to take the ISM perspective to HWO, and in particular advocate for UV spectroscopy over a wide wavelength range in order to study the life cycle of metals, and in particular dust, in the ISM in a range of environments. So as I said, we talked about the Baryon cycle, and this addresses a particular aspect of this Baryon cycle, which is within the ISM, the transfer of metals between the gas and the dust phases. We know dust grows in the ISM with timescales that depend on mostly density and metallicity, and as a result, the properties of dust vary within and between galaxy. There are few reasons why we need to study these variations and understand them. And I'm going to go quickly through this so I can get to the HST and then HabWorlds part. Number one, dust is a key component of galaxy evolution. It affects the radiative transfer of galaxies. It shields star-forming regions from ionizing photons, allows molecules to form, in particular molecular hydrogen, contributes to the heating and cooling, etc., etc. Dust is unavoidable. When you take observations of galaxies, dust is everywhere. And in particular, it absorbs the UV optical stellar light emitted in the far infrared, which for a galaxy like the Milky Way or Andromeda is about half of the energy output of a galaxy. So it's a big contribution. You can see this in the images of Andromeda on the right. Another important reason is that we want to use far-infrared emission from dust to trace the ISM at all redshifts, and in particular at high redshifts where dust emission is the only tracer of the ISM because you can't get the 21 centimeter, and CO only traces the molecular ISM. The problem is that far-infrared emission has some kind of large systematic uncertainties to convert from the emission to masses. And that's a problem. So in order to get around that, we need to study the dust composition and dust abundance from UV spectroscopy. And we can do this with HST, but also even better with HabWorlds. Yet another reason that we actually heard about this morning is to better understand dust in Lyman alpha systems. These are absorption systems that we can observe over a wide range of redshifts using quasar absorption spectroscopy. And this is one way that we can track the chemical enrichment of the universe. And we heard from Louise Welch why this is really important to observe. The problem is when you measure abundances of, say, iron in those systems, you only measure in the gas phase abundances. And those have to be corrected for depletion effects, which for refractory elements like iron can be pretty huge, even up to 1 dec at moderate metallicities. So we need to understand how this abundance of dust varies, and in particular with metallicity. Moving. Likes the delay, it's too much. Okay, all right. So how do we do this? In the nearby universe, you can kind of calibrate a lot of the dust properties. This is an example here in the Large Hadron Cloud. You basically point your UV spectrograph towards a massive star, an OB star that's bright in the UV. take a spectrum that covers both the FUV and the near UV, and I'll come back to that. This is very important. So you can probe all the metals that are in the dust grains. So going from magnesium and silicon, nickel, iron, and also some metallicity tracers like zinc and sulfur. And also we of course need the Lyman alpha line so that we can measure the hydrogen content, and ideally the H2 lines between 1000 and 1100 angstroms. From those absorption lines, you can measure abundances of all those metals, and then you can put them all together and estimate the abundance of dust in the following way. We measure gas phase abundances from Hubble. We don't know what fraction of those metals are in the dust grains, but we do know abundances of young stars that recently formed out of the ISM. And we know those from ground-based spectroscopy in the optical and infrared. JC just talked about this. Currently, this is done with telescopes like the VLT or GTC, but ultimately the ELTs will really reach much further distances of 10, 20 megaparsecs. So you know how much metals are in the gas, you know how much metals are total in the ISM, gas plus dust from the stars. You can compute the fraction of metals in the dust, and those are called depletions. Don't worry about the equations. The point is, we can know gas, dust, and total. From HST, we've learned a lot about this in nearby galaxies, and in particular, the Milky Way imaginary clouds. This is the galaxies where we can do this best. In the Milky Way, there's over 200 sightlines with measured depletions for the main elements that are the constituents of dust, like carbon, oxygen, magnesium, iron, silicon, etc. I will note, though, that there are only a few sightlines with very noisy carbon depletion measurements. Carbon's hard because the line at 30 and 30 100 angstroms is very saturated, and the weak line in the is almost never detected. With Ulysses and previous large programs in those galaxies as well, we have over 100 sightlines now in each of the LMC and SMC. So we can get depletions for a bunch of metals except carbon and oxygen, which have not yet been measured outside the Milky Way. So again, putting all those metals together, we calculate the dust-to-gas ratio, and what we've established so far is that the abundance of dust depends on the gas density because of dust growth in the ISM. You can see this in the SMC on the left, where you have dust to gas versus column density of hydrogen. It increases by a factor of 5 to 10, depending on measurements, and there's a discrepancy with the far IR, again, probably because of those convergent factors that are not well constrained. We also have some constraints on the dust composition because we can measure the metals individually. And so now we kind of have a good idea of how the dust composition varies from the Milky Way to the LMC to the SMC. We have a good understanding of how the dust abundance varies with metallicity, again, going from Milky Way to LMC to SMC. And those are shown here on the left. And you can see that, again, we come back to this discrepancy between the far IR and the UV spectroscopy. And this also tells us that, raises the question of whether we can actually trust those far IR measurements of the dust-to-gas ratio at low metallicity. We're not sure. So we need to populate this diagram at metallicity is lower than that of the SMC. And then finally, from HST, we have some of those depletion corrections for DLAs. At metallicity down to that of the SMC, which is 20% solar. I'm not going to go through this. This is kind of complicated. Basically, you establish the corrections based on abundance ratios of volatile to refractory elements. And then you can correct your DLA measurements for depletion effects. So this brings me to the limit of what Hubble can do. And as for this particular science case, it's Sextans A. As I said, we need to probe lower metallicities than the SMC. And so far, we've been able to reach basically Sextans A, only a few of these stars, and only in the shorter wavelength of FUV, so between 1140 and 1430 angstroms. That's basically the G130M grading of COS. And that's 15 to 20 orbits a pop. So it's very expensive, and the signal to noise, as you'll see in the next slide, is on great. The G160M range is basically inaccessible in the galaxy, and so is the near UV. So you can see here some of the measurements of iron, which is in the short wavelength range of the FUV that we could get in Sextans A. It's very noisy, but it gives us an idea that the fraction of metals in a low metallicity galaxy like Sextans A is much lower than, say, in the Milky Way, which would drive the dust abundance with metallicity in a nonlinear way. So this is what I mean by the spectra are kind of a little difficult to work with at low metallicity. You can see excerpts for the iron 2 lines on the left, magnesium 2 on the right, going from higher metallicity at the SMC at the bottom to the lower metallicity at the top. So this is SMC, IC1613, which is like 10 to 20% solar, Sexton Z at 7% solar, and then Leo P, which is 3% solar. There's only one star that's been observed with COS in that galaxy. SMC, no problem. We detect the lines. We can measure abundances. IC1613, still okay-ish, 10 to 20% solar metallicity. Once we get to Sexton Z, it gets really noisy. So our abundance measurements are extremely noisy, and we don't even detect magnesium at that signal to noise. In Leo P, the signal to noise is not even sufficient to detect iron. So we're kind of stuck. And so what do we need? Well, we need HabWorlds with UV spectroscopy, sensitive spectroscopy, relatively high resolution. So I'm going to work out the science case using Sexton Z as an example because it's the limit of what Hubble can do. So on the left here, you can see an image of Sexton Z in different tracers, which are indicated in the panel. And then the field of view of Lumos, for example. That's just an example. It's just going to knock it out of the park. Basically, you're going to do most of the Sexton Z stars all at once, have enough sensitivity to reach those iron and magnesium lines that I was talking about. And also the good thing is soon the LTs will come online, so we'll be able to get those stellar abundances that we need in order to calculate these depletions. So I went ahead and tried to calculate exposure times for Sexton Z stars. I took the V magnitudes, the node spectral types, modeled the UV fluxes, and then assumed that Lumos, or an instrument like Lumos that would be on HabWorlds, is 100 times more sensitive than COS. That might be a little bit optimistic. The report states 30 to 100 times. So go big or go home, right? Resolution 30,000, which is kind of in line with what we need. To get the iron lines, we need signal to noise of 20. Magnesium is weaker, so you need 70. And so these are histograms of the number of stars that for which we can observe those lines, with Hubble in red and HabWorlds in blue. So basically, iron, we knew we can only do a few of the stars in Sexton Z. With HabWorlds, we'll do them all. For magnesium 2, higher signal to noise, again, with HabWorlds, we're just going to knock it out of the park, do all the stars, done, boom. And again, for the near UV, we can't do anything with HST, in particular for the silicon 2 and zinc 2 lines. And again, HabWorlds, we'll be able to observe them all, and all at once. So this is great. I also went through the exercise of trying to compute exposure times with the Lumos ETC, which was less great, but still pretty good. At the wavelength I did the computation, it was about 6 times faster than COS. So you could do all the iron lines in Sexton Z, no problem. Near UV was more problematic, and so was magnesium. So what about other galaxies, right? Sexton Z is right at the limit of HST. Can we go further with HabWorlds? Well, the answer is probably yes. If we want to put one OB star in each of the shutters, we can actually go out to 15 to 20 megaparsecs. In terms of flux, the decrease is a factor of 250, but if we're 100 times more sensitive than COS and we can do all the stars all at once, in principle, 15 to 20 megaparsecs is perfectly doable. There are 190 galaxies with metallicity lower than the SMC within 20 megaparsecs, including ISVT 18, which is kind of the ultimate goal, I think, in terms of chemical abundances in the ISM, but also, stellar properties, even, galactic outflows, etc. So yes, we should be able to get to ISVT 18 with HabWorlds, and certainly I think we should try to push for requirements that allow us to do that. I'm out of time, so I'll leave that slide here. It's about carbon in the imaginary clouds, which we could do with Pollux, high signal to noise, high resolution. So if we could get that, we would elucidate the carbon budget of those grains, which we have, for now, no idea how it works because we don't have any measurements. And I'll leave you with those takeaways. Basically, we need FUV and near UV to cover all the metals. We need coverage down to 1,000 angstroms to get the H2. And I know the galactic outflow people also want the O6 and all that. Relatively high resolution, multiplexing for efficiency. The ability to reach high signal to noise is important. We can't really do that with COS, but if we want to get those weak lines, we will need to get to 100 or so in signal to noise. And it would be much better to have 100 times COS sensitivity than 30 times COS sensitivity. So, thanks. Take questions.
Thanks for a great talk. Any questions, anybody?
Thank you, Julia. So when you were talking at the end about getting the carbon, was that enabled by the high spectral resolution? I guess if is there a benefit to having R of 100,000 at comparable sensitivity? Like, what do you get if you get more resolution?
Yeah, right. So the carbon lines I'm talking about in UV is extremely weak. It's only been measured in the Milky Way towards a few stars with the STIS Echelle gratings, the H gratings, so very high resolution, and high signal to noise. I think it was 100, 150. So I think we really do need both because the component structure of the ISM can be pretty complex, and there's going to be some degeneracies if you don't sample that structure. But also at that point, the lines are so weak, I think that the highest resolution you could get, the better.
Okay, any other questions? All right, let's thank our speaker again. Thank you.
Thanks.
Okay, and Jason, I think the next speaker is online. Oh, you...
Oh, she's here.
Yeah. Make sure he's here.
Perfect.
There he is.
Okay, so our next speaker is, and I'm sorry if I mispronounce your name, please correct me. It's Fakhri Zahidi, who's over at Carnegie, who's going to tell us about Toward a High-Definition View of the Baryon Cycle and its Impact on Galaxy Evolution in the HWO era, sorry.
Do a screen share.
Thank you.
Do this.
Can you see my slides here? I just started
Yeah,
projecting
see them
my screen.
fine?
Why don't you make them full screen and then we'll get the whole picture.
Okay, awesome. And you can hear me all right, I assume?
We can see them and we can hear you fine.
Okay, great.
Hit it.
Okay, great. Okay, so I'll start, I suppose. Okay, first, good afternoon, everybody. I would like to thank Jason and Neil and the rest of the organizers for accepting my contribution. It's been a great meeting, learned a lot. I was glad that Chris Hauk actually gave his talk yesterday because he did a brilliant job setting the stage and outlining all the important questions that HabWorlds can answer for my field of the CGM. So you heard a bit from Chris yesterday, so I'll start by just reiterating the importance of this idea of the baryon cycle and its role in galaxy evolution. So while dark matter provides the scaffolding, the skeleton around which galaxies and structures can form, it is actually the baryons that explain the huge diversity of galaxies and galaxy properties that we see today. So this figure summarizes how the movements of baryons in and out of galaxies are so intertwined with galaxy evolution itself. We have inflow of gas from the IGM that feeds star formation and the growth of supermassive black holes. And then star formation can drive outflows that then push energy, momentum, and heavy elements out of galaxies into the surroundings, which can then regulate future star formation activities and enrich the universe. So understanding the physics that drive this baryon cycle is really critical to understanding and completing our picture of galaxy evolution. Now, the circumgalactic medium is really where most of these processes take place. So what you're seeing here is a nearby spiral galaxy M81 and its major satellites. You can see M82 there. And this is how it just looks if you just look at the starlight. But immediately you see a very different situation, a much more dynamic picture in a 21 centimeter map emission of the same system. So you're looking at neutral hydrogen gas here, and you see a very complex environment. So what we see here is this exchange of gas between galaxies and the surroundings. You see M82 on top driving powerful winds that expel heavy elements out of it. You see these different galaxies interacting with one another by gravity, and that interaction can strip gas from them. You see tidal bridges, you see gas streams. So in many ways, this baryonic process is really galaxy evolution itself. So as you heard from Chris yesterday, the most powerful way to study the CGM is really through the absorption that the gas of the CGM imprints in the spectra of bright background quasars. You see a series of absorption lines imprinted on the spectrum of the background quasar by the foreground gas. I'm showing you here examples from my own work, and it is from studying the detailed profiles of the absorption here using high-resolution spectra that we can learn a lot about the physical properties of the gas. The line of sight velocity relative to the galaxy will tell you something about how it moves. The width of the lines will tell you something about the temperature and the amount of turbulence in the gas. And then the relative amount of one element to another will tell you something about the chemical composition and the ionization state of the gas. So using the absorption line technique, we can then look at different absorption species from different elements that are present in the CGM. And each of these probe different gas phases, densities, temperatures, etc. in the CGM. So you saw this figure in Rachel's and Chris's talks yesterday, showing how the various ions we detect in the CGM correspond to different regimes in the CGM temperature and density phase space. And as you can see here, the CGM is a multi-phase medium that spans multiple orders of magnitude in densities and temperature. The most important takeaway point from this figure is this. If we want to build a robust physical picture of the role that the baryon cycle plays in galaxy evolution, we need access to all of these different phases, not just any one of them. We need all of them. And for the majority of the universe's history, most of these phases are traceable only in the UV. And that's why it's essential that we continue to have access to a sensitive UV spectrograph in space. All right. So one of the main challenges in studying the CGM is figuring out the physical origins of the gas. It's kind of the holy grail. It's not that easy, actually, and I'll illustrate why. So let's say we detect gas 100 kiloparsec away from this or that galaxy. How did it get there, and where did it come from? So one of the main observables that we observers can look at is the chemistry of the gas. So this figure I'm showing right here summarizes the state of the art on CGM chemistry. This is based on work I led with the COPS collaboration using the HST in the UV. So we've invested 100 plus orbits for this. So this is showing in blue points various elemental abundance ratios that we see in the CGM as the function of the absolute metal abundances on the x-axis. And superimposed on it are the same quantities plotted for both stars and ISM gas in different types of galaxies. As stellar spectroscopists would know, this kind of plot can be used as a clock to tell you something about the enrichment history of the gas, because the horizontal direction goes along the direction of increasing chemical enrichment or increasing metallicity, whereas the vertical arrow signifies increasing chemical maturity, chemical evolution. So what we can use this for instance, is if you're looking at gas which has similar metallicity and similar elemental abundance ratios as you find in a nearby galaxy that you have identified, then, and that galaxy happens to be strongly star-forming, then from a chemical argument, that's strong evidence that you're looking at outflow. On the other hand, sometimes we see CGM gas which appears chemically evolved. That is, it's high on this vertical axis here, but it also has low metallicity. It's displaced from this main distribution for stars and ISM gas. And like I'm circling there. Now, this is very interesting because it may be evidence for chemical dilution, where you have gas that is previously, it was in a galaxy, but it has since been ejected and then mixed or diluted with low metallicity gas from the IGM. So this is how we can use the detailed chemistry of CGM gas to figure out the origin of the gas itself and how it ties physically to galaxies in the environment. But that's not all. The other major way that we can connect the CGM to galaxies is through the kinematics. I know Chris was asked about this yesterday, so I want to reiterate this. It's very important to realize that interpreting CGM kinematics is a non-trivial issue. The classical approach to study the CGM is using single background line of sight to study a foreground galaxy. It's a one-dimensional pencil beam approach. What we don't get from that is direct spatial information. The only thing our data tells us is whether the gas is blue shifted or red shifted and how big that shift is. But without any spatial information, there is an inherent degeneracy between whether it's outflowing or inflowing. Let me illustrate. In principle, a gas that is outflowing in front of a galaxy can manifest the same blue shifted kinematics as a gas flow that is actually infalling to the same galaxy but behind it. Granted, this is a spherical cow version of the problem, but the point stands even when you deal with actual data. there is a degeneracy here that single sightline studies cannot break. We need spatial resolved data of the CGM in order to do that. And so this need to start doing spatial resolved studies of the CGM was recognized actually in the latest decadal report, which I was very happy to read. It's essentially saying, and I'm quoting here, that the CGM is so complex with things happening on multiple physical scales that understanding it requires observing it in a spatially resolved way. So one of the recommendations is a large space telescope, which would allow observation spectroscopy in the UV of a much higher density of background quasars. And this is precisely what we hope HabWorlds would be able to do. Now, with HST and the smaller size and cost, this kind of investigation could today only be done with a very small number of the nearest galaxies. An example I'm showing here is from Project Amiga, which is led by Nicola Lehner and Chris Haug, and they used around 40 lines of sight towards M31. A Herculean effort, hundreds of HST orbits invested, of course, which is great, but in the future we have to do this with just more than one galaxy. And that's something that a bigger telescope like HabWorlds would be able to do. With HST and cost, we normally have to limit ourselves to quasars around 18th magnitude or so in the far UV, perhaps 19th if you're pushing it, but this gets expensive very, very quickly in terms of the number of orbits you need. And there aren't very many of those UV bright quasars anyway, less than 100 at 18th magnitude or brighter. And so the good rule of thumb to remember is as follows, because of the quasar luminosity function. When you double the number of background quasars available to you for every half or so magnitude increase in depth. So what that means is, with a 6-meter class glass in space, we shall be able to reach up to 21st magnitude easily with a reasonable number of hours. So I'm illustrating here M51, a nearby star-forming galaxies, where HabWorlds would give us access to 30 plus background quasars probably in CGM at less than 21st magnitude or so in brightness. And not only that, we will be able to do this kind of investigations for hundreds of galaxies within the local volume of all types, sizes, star formation history, and environments within the inner 10 megaparsec or so. And I think this is what we're waiting for HabWorlds to do in the next 20, 30 years or so. The catch, however, is that HabWorlds will not be here for quite some time. So what do we do then? Well, my workaround while we wait for HabWorlds is to start spatially resolving the CGM using lens quasars. This is general relativity in action. It's what happens when light from a distant quasar at high redshift happen to be lensed over a massive object, like a massive galaxy between us and the source. And this lensing creates multiple images of the quasars on the sky. So what this gives us is basically the ability to probe the gas in the CGM at multiple locations per galaxy and study the spatial variations of the gas properties over kiloparsec scales or so in the CGM. And the best part is you can study this for the CGM of the massive galaxies in the center, or really any galaxies that happen in projection near the lines of sight, like these two I'm showing with the box right here. We know about 300 lenses today, about 50 bright enough to be observed in high resolution with current 10-meter class telescopes in the optical, and in the future with HabWorlds. Fewer than 10 of these we can do with HST today, and that's in low resolution mode. That's just how it is. So one of the things I've spent a lot of time over the past several years is to build the spectroscopic sample, the largest one of lens quasars. I've observed about 40 of these with 10-meter class telescopes and obtained high-resolution optical spectra of them. So I'm currently working with my collaborators to do a deep spectroscopic survey of these fields to identify and characterize the foreground galaxies in the CGM. And this is an area with a lot of growth potential because by the end of the decade, we will know thousands more of these lenses thanks to surveys like LSST in the near future. So now I would like to show you what we can gain by doing these spatially resolved studies of the CGM. These are very recent data that I got recently, and I want to illustrate the kind of wealth of information that you get from studying these lenses. So what you're looking at here is HST I-band image of a field around a quadruple lens quasar. You can see there, it's a diamond. The lens itself is at a redshift of about 0.6, but what I wanted to pay attention to is the galaxy in the circle. That's a star-forming galaxy at a redshift of about 1.6. And this panel here shows you high-resolution optical spectra of the four lens line of sight, the A, B, C, and D, as you can see there, for magnesium-2 and Rn2, centered in the galaxy's rest frame. In addition to these four transverse lines of sight, the galaxy itself shows strong down-the-barrel, blue-shifted absorption self-absorption in these ions. And that's great because it confirms that this galaxy is driving a strong outflow. So these profiles are complex, as you can see, but even upon simple inspection, you can already see some similarities between some pairs of lines of sight. For example, A and C here are closer to the galaxy, and you can see that their profiles are complex, has more kinematic components at a wide range of velocities. B and D, on the other hand, are farther away, and in comparison, they look similar and simpler to each other, simpler than A and C. At the same time, the chemistry appears to be different. It looks like there is a lot more iron in B than in D, and in A than in C. So it looks like there is some azimuthal variations here as well. So what really excites me is we can use the detailed kinematics and the chemistry that we see across these 5 lines of sight to not only constrain the geometry and the energetics of the outflow itself, but also answer questions like, is it accelerating or is it decelerating with distance, and how so? What is the geometry, the opening angle, etc.? And does it change with redshifts and types of galaxies and galaxy masses? So in the future, HabWorlds would give us access to H1 and more metal species, including high ions, and it would allow us to study these things in more details, to get metallicities and to understand the ionization properties of the gas. Because so far, we can only do this from the ground. So I'm almost out of time, so I'm just going to end right here. And just summarize, I hope I've convinced you that spatially resolved CGM studies are the future. I'm so excited about how my field is going to evolve in the future once we study the CGM routinely in this spatially resolved way. And using lens quasars today, we can already begin to characterize the physical properties of the CGM gas flows over cosmic time. So we can understand how the baryon cycle influences the growth of galaxies over time. And in the future, HabWorlds would allow us to perform full-scale tomography of the CGM of hundreds of galaxies in the local universe and thousands more at high redshift, so potentially revolutionizing my field. And we definitely need a high-resolution, high-performance UV spectrograph for that. Thank you.
Thank you. Let's take a question online.
Yeah, so we have a question online from Mark Elowitz, and the question is, would it be possible to use the sight lines of closely spaced background quasars to search for correlated absorption in order to model the 3D structure of the intervening gas clouds?
Absolutely, yes. So I have a backup slide for that, actually, so I'm just going to show it right here. So yes, you can. In fact, one of the most exciting applications of lenses to study small-scale structures of the CGM, to do something like what's the sizes of these CGM structures. And this is a very important question because if you're somebody who simulate these things, people like Molly people's there, you want to know what kinds of resolution do you actually need to get down to in order to really model these CGM gases in a physically sound way. And so you can use these lenses and look at how variations in gas column density or gas kinematics and the gas chemistry actually look like as you go from large to small separations. And this is something that we can do actually. And I think insight from models would be very helpful to this. But at least from the data side of things, it looks like there's a physical scale below which you don't see much variations in chemistry or in kinematics or in the amount of gas that you see as you go towards one line of sight from the other. And that scale appears to be around 100 parsec or so. And but this is something that I will continue to investigate with new data coming, but it looks like you don't need to go down to like 10 parsec or so or something like that, but 100 parsec seems to be a good figure of a good number to aim for if you're trying to simulate data. But yes, the answer to your question is yes.
Okay, thank you very much. Let's thank our speaker one more time. Okay, our next presentation, we'll hear about far UV star formation by Alina Sabi.
Can you hear me? Yes, you can. Great. Okay, so we've heard about the importance of spectroscopy to understand massive stars. I am going actually to look at photometry. And I'm going to try to show you how important it is to use far and near UV observations to characterize the region of massive star formation in nearby and more distant galaxies. I don't know how to go forward. Let's see. Nope. I broke it. Okay, it's going. Okay, so one reason why we want to understand the light from massive UV stars is because this is what we see at high redshift. And right now we are having an issue that we have an excessive count at redshift higher than 9, according to Webb. And it is not, and this excess is contradicting both the projection from the current cosmological models, but also the estimation that we get from low redshift galaxy counts. One possibility is that maybe our cosmological models are wrong. Another important aspect, however, is that we still do not understand the property of dust and the stellar evolution in the local universe. We don't know the properties of the IMF. We don't know if there is an upper mass cutoff, at what mass it is, and so on. And we had a beautiful introduction before, so I don't need to give you, I don't think I need to convince you, but I want to show you what we don't know. So to try to understand the properties of star formation, we looked at 23 star-forming galaxies using Hubble in the far UV and the near UV in imaging. We used the solar blind channel, and because the solar blind channel is very small, we actually mosaic across the galaxies. We tried to cover the broadest range possible in terms of metallicity, star formation rate, mass. This is the parameter space that we are covering. The larger symbols are the galaxies that we target within 8 megaparsec, and this is roughly the best we can do so far if we wanted to have an efficient program. The galaxies are color-coded in terms of metallicities, and we already, within 8 megaparsec, we start to have an issue. We are not covering all the metallicity range. We have a lot of low metallicity galaxies, but they are not very they don't have very high star formation rate. We have high star formation rate galaxies, and they are high metallicity. So we are not covering the entire parameter space. If we wanted to get, for example, the super star burst like 1ZK18, we have to go to 20 megaparsec, and so on. The gray point are all the galaxies that are in the 11 HAGS survey within 8 megaparsec. So we are not, again, covering all the galaxies that we would like to cover. And the 4 points in cyan are the Ulysses targets. So again, we don't have all the templates that we would like to have to characterize the properties of the redshift universe, but we start to have a good template. The galaxies that we selected have also observations in the archive in all these filters. So in total, when we combine all the data, we get 8 filters. And the goals are to try to understand the stellar IMF, the properties of young massive clusters, and, for example, understand what is the impact of dust and how it behaves in different environments and metallicities. These are examples of the galaxies that we cover with GOLP. And this is the team that is working on this project. And in particular, I would like to highlight the work that Bina Amina, the postdoc that is leading this project here at STSCI. So why do we want to study these galaxies in the far UV if they are already so well known in the optical? Well, the reason is that basically all the stars saturate massive stars in color at a wavelength shorter than B band. So we can basically not discriminate any of these properties. We don't know the temperature of these objects. We don't really understand their behavior. And then when you start to add extinction, things become even more complicated. Basically, a 25,000 Kelvin star is identical to anything in this range here when you start to have extinction. One way that can help us is, for example, to break the degeneracy using the bump. And so we can start to sample different type of extinction in the various wavelengths. And if you have a good handling on the extinction, we can start to break the degeneracy and start to give a more accurate age to your population, start to trace the formation of your galaxies with a look-back time of about 30, 40 million years. So, but you can trace it very well. So this is what we know about galaxies thanks to GALEX. This is NGC 4449, and this was the best resolution we had in the far UV until a couple of years ago. This is what we can map with the solar blind channel if you combine the various exposures, and this is how then your data look like. So you can start to resolve the single stars, and you can start to see that in a region like 4449, that is a galaxy that went through a major starburst about 20 to 30 million years ago. You have a very rich populations. You can distinguish multiple star clusters in the centers. There are 2 major star clusters. You can see how different and rich the environment is. Normally, for convenience, galaxies are studied with photometry in this color magnitude diagram, I versus V minus I, and that is because it gives us the best look-back time. We have populations that are as old as many billion years, and then we can trace the properties of the massive stars. But as you can see, everything is very compact. And if you really want to understand the recent star formation, you need to move toward bluer colors at the cost of the resolution, at the cost of the look-back time. The red giant branch here is already completely folded, and as you go bluer and bluer, what you really resolve are the property of the most recent episode of star formation. One nice, interesting thing is that you can start to really separate well the main sequence from the blue edge of the helium-burning stars. If you have multiple filters, you can also start to do relatively accurate SED fittings and try to characterize the physical properties of the stars. This is what you get if you assume single stars evolutionary tracks. Most of this, you have the main sequence here, the evolved area here, and then you have the candidate Wolf-Rayet stars up here. However, as we heard before, binaries are actually an important component when you try to understand the properties of massive stars. According to Kinney in the Milky Way and Sana in the Magellanic Clouds, when you go above 10 solar masses, most of the stars are in binaries. And then your evolution becomes much more complicated. We use the code by Jan Eldridge and Elizabeth Stanley to try to interpret our data. And this is how the HR diagram varies when you start to induce binaries. The orange points are the companions of the binaries that you get in your data. And you start to see that, first of all, we didn't have an indication of red supergiants, but we have a series of sources that have an excess in the I band. And they are likely red supergiant binaries. So one star is in the red supergiant phase, and the companion then is still in main sequence. And also, we have this weird population of objects here that I will mention later. Depending on the assumption that you made on the dust, your solution changes. So this is what you get if you assume a Milky Way-like extinction, and this is what you get when you go in the SMC-like extinction. And the points are color-coded depending on what is the best solution for the SED fitting in at least 5 of the 8 filters that we have. Although there is some degeneracy with the models, some results are more robust than others. So for example, we get a very good handling, or at least all the codes agreed, all the simulation agreed on the age of the population. And the size of the point here is proportional to the mass of the sources. And this is where they are in the various color magnitude diagrams. As you can see, it's not very easy to identify an evolutionary phase to say, oh, this is the point, this source belongs to this point. However, if you believe at the ages that you're getting from SED fittings, you can start, for example, to follow how your populations start to dissolve in the field of the galaxies as you're looking back in time, as you're looking at older ages. So basically, we are rediscovering the infant mortality of massive clusters. However, if you use a clustering technique like, for example, ACDV scan, you can also try to measure how fast your populations are dissolving in the cluster. So this is the work that Bina is leading so far, and we see how fast in the galaxies the structures are dissolving, are disappearing, and also we can test that as the minimum separation between the various sources, so the population becomes also less dense. Another interesting result is that, at least in NGC 449, the structures are not dissolving in a uniform way. They have a preferential direction that is aligning with the spiral arms and the bar of the galaxy. This is a starburst galaxy. It's a very perturbed system because it's in interaction. We want to see what happened, for example, when we look at regular spiral galaxies and what happened, for example, in dwarf galaxies that have much lower star formation rates. Interesting sources that can be detected using SED fitting are, for example, the Wolf-Rayet. We have stars that are already have a considerable amount of helium in the core, and also, and this appears only if you assume binaries, we see that a series of objects are compatible with having already the degenerate companion, so either a white dwarf or an evolved object. And when you see where they are in the color magnitude diagram, it's not so simple to identify them. So simple two filters photometry is not enough. You need much more color resolution. The situation becomes even more complicated, as I mentioned before, when you look at peculiar objects like the binary with a red supergiant and main sequence stars. And then there is this population here that are binaries where one of the two companions has lost its outer layers, the strict binaries. These are predicted by binary evolution. In the Milky Way, we have one candidate so far that seems to be the right object. They are very hard to find because in the color magnitude diagram, they are blue objects with the UV excess, so it's not very easy to find them. However, these objects are very interesting because they transfer to each other the outer part. So they start to show us the inner part that has been where the more processed elements are. And they also release a series of interesting elements during their various pulsating phases. So they have an impact on the properties of the ISM, and understanding how frequent these objects are, it's important. As it is important, for example, to know how many are the objects that are going to interact in the post-main sequence phase, because those are the progenitor of, for example, gamma-ray burst and gravitational wave sources. The only way that we have to confirm those objects is through spectroscopy, by the way. I promised that I was talking also about the infrared properties. This is what we can study in the optical, but the early phases of the clusters are embedded in dust, and so we needed to look at them in the near infrared. With Daniela, we studied the same galaxies using the IR channel of WIPC3, and we found a population of objects that were not identified. These are massive clusters that were not visible at wavelengths shorter than F555W, the V band. The populations of all the massive clusters present from the near UV to the I band were studied by Whitmore et al. For these galaxies. And then this population found here are strong emitter in Paschen alpha, and they're not visible, as I said, at wavelengths shorter than the V band. We don't know exactly what these objects are. Based on SED fittings, they should be star clusters that are older than 5 or 6 million years. And this is puzzling because they are maintaining a huge amount of dust around them. And this is how they get so extinguished. And this is contradicting all our models for pre-supernova and supernova feedback that should clear out all the environment. Ooh, I'm super late. Okay, so I'll stop. We are studying these galaxies also with the JWST. It's very pretty. And sorry. And last things, okay, if you really want to understand massive star formation, you need a multi-object spectroscopy. High resolution, 60,000, I would appreciate it because I want to see the line of the binaries moving. And I want multi-object because I have a lot of stars to study. Thank you, sorry.
Thank you very much. Any questions?
All right, I'm going to put you on the spot. What is the spatial resolution you need in the ultraviolet? And I ask because we probably won't be diffraction limited at those wavelengths.
A lot. Better than near spec. Oh, no, you promised me a lot of spatial resolution. You gave me the plot where you were, put your pin and choose your stars. I want that. I believed you.
All right, any other questions? All right, let's thank our speaker again.
Thank you.
Okay, our next presenter is Andrea Petrick from here at Space Telescope, who's going to be telling us about obscured AGN, hiding high growth at the cosmic noon. Thank you.
Thank you. So it might not be cosmic noon. It could be cosmic evening or dinner, coffee break. Yes. So when I set this up, I will tell you my conclusions. So, yes. All right. Thank you. So I will use this then. Okay. So my conclusions are that obscured AGN are a key population to study for understanding how galaxies grow and how black holes form, are a key population to study how the growing supermassive black hole impact not only the interstellar medium, but also the circumgalactic medium, and also the role of mergers in galaxy evolution. And what we need for this is spectroscopy, 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 and that's spectroscopy in the near-infrared, spectroscopy in the optical, and spectroscopy in the UV. What would be ideal and wonderful would be to also have spectropolarimetry, and then we will understand everything. So one of the questions that have been guiding astronomy for decades is where did all those black holes come from? How do they grow? When they grow? And one of the main ways of addressing that question is just by having an accurate census of their masses and their growth rates. And of course, if you want to have an accurate understanding of their growth rates, you also need to find the ones that are obscuring their growth with dust. And this reminded me of, Julia just left for this, and I just wanted to thank her for also being a fan of dust, because dust is an important feature in dusty AGN, as it carries this, the energetic signatures of how the AGN is inputting energy into the interstellar medium. So already with the Spitzer infrared telescope, we were able very painfully to look at mid-infrared selected AGN, follow them up with hours and hours and weeks of ground-based spectroscopy to figure out which one was a true AGN and what were their reddening properties. And once we did this, we found that the obscured AGN were evolving differently than the non-obscured AGN. And more significantly than that, their number evolution was not going down as Z2 equal 3. So we could have predicted already those exciting little red dots that Kate Whitaker told us earlier in the day. So the little red dots may be some of those continuing population of obscured AGN. But what we need to do, of course, to study them further is to see what are their host properties if there are AGN, and how do they, what are their accretion rates, and how do they interact with the interstellar medium. So the reason we are interested about this interaction with the interstellar medium was very well explained by Rachel Somerville. You want to understand that the multi-phase feedback in a multi-scale way. And so you need to look at things in obviously different scales, but also different kind of obscured AGNs, going all the way from luminous infrared galaxies that are luminous in the infrared, to high luminosity obscured AGN at high redshift. And so the reason we're interested also in them is that it may probe a specific point of galaxy evolution, one that we will, and by we I mean, you know, if we have 5 billion years to stare up at the night sky and see Andromeda come over, then our black holes may merge, and who knows what AGN may come out of it. But another point that this movie was making is that through the dust, you can already see that some of the star formation are peeking through, that the interstellar medium is not smooth. And Claudia made an excellent point of that, as when you have your interstellar medium impacted by stars, by an AGN, and punching holes through it, you will be able to see the UV, and you will be able to see optical radiation. You will be able to see all the phases of the feedback. So the future is bright, the future meaning partially the present. And in the next few slides, I will give you a little bit of the astronomical landscape that the Habitable Worlds Observatory is coming into. So eROSITA in particular is excellent at finding obscured AGN. So we will have millions of them with poor spatial resolution, but that's okay because Roman, JWST, and everything else will give us the resolution. Then to understand the energetics of the AGN, it's also important to find them in the radio. And the square kilometer array will, including the precursor surveys that are covering this, will give us information not only as luminosities, but also spectral indices who are helping us age the population of electrons and figure out kind of the age of the source of the AGN itself. At Space Telescope, I'm in the Roman telescope branch, so I'm excited to tell you what Mark said to us in the first day, that Roman will be amazing. And also equally as important, it will be on time and on schedule, setting the path for the Habitable Worlds Observatory. But we will also have facilities on the ground. So you know about the ELTs, but I'm also here to tell you about the massively multiplexed spectroscopic missions that are coming. As several people pointed out, when you are on Earth, you have an atmosphere. And when you have an atmosphere, that atmosphere is not friendly to near-infrared spectroscopic observations of faint sources, which are below your sky level. And so that is a challenge. It is not an insurmountable challenge, but it's certainly easier to be above. But what this means is that we will have at that point in the 2030s, we will have large surveys of AGN for which we may be able to already find the star formation histories or the multi-phase AGN. But those will not necessarily be MOS capabilities and will be near-infrared optical. And so will those answer the questions that I start with? Of course, since I'm giving a talk to this Habitable Worlds, the answer is no, they will not answer it. And the reason for that is because we are will be missing the significant component of the UV gas. The most ionized, the structure of the most ionized gas is the gas that's actually connected closest energetically to the AGN. So you have to count basically all your photons. You have to see what goes in and then what goes out of your dust that is doing the obscuration of your obscure galaxies. So now in the next few slides, I'll motivate a bit why do we care so much about this multi-phase ISM. And whether does the ISM even care about a tiny AGN. And so the answer is yes, it does. And we've seen this in a large number of types of sources. So for example, in luminous infrared galaxies, which are nearby, are big, they have a lot of weather. And by weather, I mean there are 50% above 10 to the 11.5 infrared luminosity are mergers. So the new star formation associated with tidal tails, the outflowing and the inflowing gas, makes observing and studying luminous infrared galaxies exciting but complicated. But what we've seen when looking at the warm molecular gas, so this is gas that we observe in rotational transitions in the mid-infrared. The thing that mattered the most was whether they had an AGN or not. It was not the merger, it was not the mass, it was not the star formation, it was whether they did or did not have an AGN. But this was for luminous infrared galaxies, and you might remind me that only 20% of luminous infrared galaxies have an AGN that contributes significantly to the bolometric luminosity. So then what we want to do, as Julia said, go big-ish. And we did by looking at all the Spitzer, all the AGN that Spitzer observed, and doing the same exercise of looking at the rotational molecular gas. And what we found was a statistically significant result that the AGN had warmer gas and the non-AGN. And we did a lot of comparison with merger AGN and non-merger AGN, and merger non-AGN and non-merger AGN, and other similar combinations to identify whether the more significant factor was the presence of the AGN. And it was. And of course, JWST revolutionized the field, because now not only are you able to get the molecular hydrogen in the whole region, but you are able to trace how it evolves as a function of AGN. So far, those are observations with MIRI MRS from the JWST Goals team. And it's an exciting appetizer of what JWST will be able to bring us, but it's an even more exciting appetizer about what Habitable Worlds will be able to give us. Because with it, we would not only be able to trace the warm molecular gas, but also the hot ionized gas and the hot ionized gas kinematics. So then you can combine the kinematics of the warm gas with the hot gas. So you know what is the energetics and what movements are happening inside the galaxy. Luminous infrared galaxies, as they are obscured AGN since they have a lot of dust, and RC52s, are also good laboratories for studying the impact into the circumgalactic medium. Here you have an example, Markarian 266, a dual AGN host, and what's most exciting about this is that when we look with spatially resolved optical spectroscopy with an 11 by 11 arc-minute FTS on the ground, you are able to trace with poor resolution, but you are able to trace highly fast movement O3 that goes all the way to 20 kiloparsecs in that super wind region. So that tells you that those kind of sources are able to kick out some of the material into the CGM. So I said luminous infrared galaxies. When you hear that, you will think, no UV. Yes, UV. So the second bump bump on this SCD is actually the UV. So we can see them, and something like Louvois can do an excellent job at finding them. So my last two slides are the capabilities that we want, which is UV spectroscopy to trace the hot gas, and spectropolarimetry, because you've probably all heard about the unified theory, the donut, clumpy molecular dust donut, and smooth smoking. There are many names for this donut, but the point is that you can scatter the broadline emission, the emission that is most impacted by the AGN. So we want to study this gas, and a spectropolarimeter will give us this. We don't need the resolution of 30,000. We can do it 200, sorry, but we can always smooth. So thank you, and I'll take questions.
Thank you very much. Any questions? Are you sure? Okay.
So you are proposing also observations in the infrared?
Near infrared, yes.
Near infrared,
yes.
Until 2 microns or something.
Yes, of course, 2 microns. And we do have the same interest, which is the raw vibrational lines of H2, because the rotational ones have a low critical density, which means that you lose all the shock information. But the raw vibrational ones in the near infrared, those are awesome because they tell you about shocks.
But these are larger wavelengths, like 3 microns or something.
The 1.2, 1.7, and you can do also with the ratio with the Paschen lines, and that's also an indication of shocks, yes.
Okay.
Okay, thank you. Let's take a speaker again. Okay, and I think our final talk is online, right, Jason? Okay, so our final talk is by Sanj Borotaka. Please correct me if I pronounce your name wrongly. I'm very sorry. And the talk will be titled Characterizing Extended Gas Disks of Galaxies in the Last 5 Gigayears.
Sanj, you out there?
Hi, can you hear me?
Just getting your screen share ready. So, Sanj, you should be able to share your slides now.
Yeah, I think I did. Can you see them?
If you just make that full screen, we'll be good to
go. It's full screen on my screen. If it's not, then I can.
Yep.
All right.
All right. It looks we can hear you and see the slides. Thank you.
Thank you. First of all, my apologies that I am not there in person, and thankful that I have been given this chance to talk online. So hello from the other side of the world. I'm talking from Seoul. A very good evening to everyone. This is the last talk, so I don't want to take up a lot of your time. It's not very technically heavy, but I want to sort of motivate people to think about these extended disks and circumgalactic medium, which is the gas surrounding galaxies, and to sort of think about our science, whatever you're doing, whether it's cosmology, whether it's star formation, planets, or AGN, the disk generally has a very important role to play because that's what is feeding the processes that go in the smaller scale, or the cosmic web is feeding the disk. So whichever way you look, the disk sort of sits in the center. So I hope that I can motivate you to think about these broader questions, and in the future, we can have a synergistic growth of our fields. To begin, I wanted to start with this press release from quite some time back. This is a very nice illustration. I think it's probably in one of our intro textbooks, which shows how a Milky Way type galaxy looks at different times. And this is kind of why we study, looking back, how things have grown. And from the point of the Habitable Worlds Observatory, one of the things that I want to stress is that if we want to study at least structures like the solar system, where at least we know one habitable world, we might be looking at galaxies like the Milky Way when the solar system was forming about 5 billion years ago. So around redshift 0.45, 0.5. And I want to stress this because at redshift 0.5, most of the lines that we can look for, especially tracing gas and metals, they lie in the ultraviolet. And that's why I'm going to push for ultraviolet in this talk, and that to spectroscopy, because we want to know about all the different elements and how they're, what's their ionization state and the structure, etc. So in that context, I believe that whether we are studying planets or AGN or big structures, all of it is connected through the disk because that's feeding the galaxies. So I think one of the simple things that people have been asking for a really long time, and this is not a very young field, is what is supporting galaxy growth, especially in terms of star formation. And people have studied for small galaxies, big galaxies, all together, all sorts of galaxies. But one of the main things that folks have found is that galaxies have these large disks that are generally seen in 21 centimeter H1 in the radio. And this was just an example cartoon showing the 21 centimeter. The background here is the optical. But the main point is that this is a dwarf galaxy, but this is something you see for all kinds of galaxies. Not super common for big L-star kind of galaxies, but large disks have been seen. Whether it's detected in alpha or VLA, you can find these disks which are much, much bigger than the optical disk. And presumably this is where the material is that is fueling star formation. And that sort of brings me to the question that when we look back at redshift 0.5, can we see a disk like this for a Milky Way-like galaxy, where the material for our own solar system comes from? And the answer to that is to look for these extended disks. The problem is that radio studies get really difficult because it's an emission line study, and 0.5 is kind of far for radio studies. But what we are trying to understand is this disk support system. We can do it with another technique by looking for these extended disks, which we believe is beyond the radio and the optical disk. There exists something more, and those are the diffuse extended disk and the circumgalactic medium. Since it's the last talk and people are sleepy, I want to come up with a question. I want you to guess, what is the size of the rotating disk, gas disk of this galaxy? This is NGC 99. It's very similar to Milky Way in kind of mass, etc. So, and it's kind of isolated in that sense and not interacting. So what do you think would be the size of the rotating gas disk? You can choose the answer if you take out your phones. You could tell I teach introductory astro level course. So if you please take out a minute, you can scan this QR code, and that will take you to a screen that has all these options. So you could probably just pick one of them. Let me put the slide back. Now the QR code is a little small. If you like to type in my name, it's going to give you a practice of spelling my name, but nothing useful. But I think the QR code is more easy. You could just pick which circle, which color circle you think will be the size of the disk. I'm actually taking a minute off from here, and I'm going to go to the poll and share my poll results. I'm not sure if this works. Okay. Not sure why I don't seem to have any responses. Anyhow, if you see this, if you click on it, you should have the. All right, in the interest of time, I'm not going to do this, and I'm going to move on to.
Can you refresh the page? There look like 23 responses there.
Oh, awesome. Thank you. All right. So the winner is yellow, followed by orange, red, and green. So let's see what's the answer. Okay, so yellow was the thing. I'm not going to give you the answer. I'm going to make you wait for a few more slides. But I'm getting a little nasty here. Let me just make it full screen though. All right. So I think, how do I know that? I'm going to just give you a little bit of hint. You have heard this, so I don't want to harp upon the technique. But what I want to stress is that one of the easiest way to look for things is in absorption, because it can trace much fainter gas. And this is what we are doing here to get the size of the disk, looking at a background source. But one of the points that I want to stress is that when we do quasar absorption or any kind of absorption spectroscopy, the very powerful thing about it is it's redshift independent. Unlike emission studies, you could look at any redshift and your sensitivity is not dependent on the redshift. It's just dependent on how much flux is. It's a fractional decrease in the flux. So we can do this as redshift 0.5 or 5 equally well. Of course, there won't be any bright sources at probably 5, but technically it's a very, very robust system, and we do not have to worry about distances when we do something like that. And of course, we get kinematics. Previous speakers have talked about it, so I'm not going to go into this. And the motivation, I'm going to just show you this quick video, is that we believe that the galaxies, if you look from outside, we believe that there is all these floating clouds. And that's what we are trying to see, how these clouds are connected to the bright stellar disk that we can see very easily in optical. Moving on, before I get to my answer, I'm going to keep you waiting for a couple more minutes. One of the things that we have noticed, and I want to highlight this, is if you look at the outer circumgalactic medium, abbreviated as CGM here, what you see is that depending on how much gas is there in the inner disk, that is visible in radio, 21 centimeter, so that's really the high density material, the outer CGM, which is about 200 kiloparsecs away from the center of the galaxy, where we actually sort of we don't see anything, has a very good correlation what is there around 20 kpc in the galaxy. And these are stats that show that. So if the galaxy has a lot of gas in it, then we see a lot of absorption in the Lyman alpha tracing the CGM. If there is not enough ISM in 21 centimeter, we see much lower. And this is translated into this model that the circumgalactic medium has clouds, and their covering fraction and numbers sort of changes as we see different levels of clouds in our own sky. So that sort of hints at some kind of a feeding process, that the disk somehow is being connected very closely to the CGM, and these material might not be flowing at ballistic speeds, but gradually coming towards the disk. All right. So coming back to the question, this is again NGC 99, and I'm going to show you the quasar and give you the answer where this quasar is at based on those different rings. But the interesting thing is, here is the optical size of the galaxy. The 21 centimeter disk is that big. I have a quasar that's much, much further out from the disk. But if I look here, I find absorption, very strong absorption in Lyman alpha. Well, absorption is strong, but column is much, much lower, 10 power of 14. The 21 centimeter traces up to 10 power of 19. So I'm 5 orders of magnitude down. But what I see is that it's exactly the same velocity as the size of the disk it's rotating. All right, so to give the answer, the quasar that I'm looking at is at this point in the orange circle. I cannot say the disk doesn't extend further, so maybe the red is also right, but certainly we do see that something is there out to the orange circle. And I think it's a disk. I'm not going to show you data. I'm going to you have to trust me on that because we don't have a whole lot of time, but we do this for about 32 galaxies and we always find co-rotating material. So I believe that the covering fraction is really, really high, about 90% or more. And as a result, what we think is happening is that this must be this large extended, either a disk or maybe a thick disk or a cylinder-like thing. Something is rotating along with the disk. And that's why I believe that it's only one sight line, but probably it's very well volume covering. Covering fraction is high. All right, I'm not sure how much I have, but I just wanted to show that simulations predict these things, extending up to 200 kiloparsec, and they are what simulators have seen as essentially feeding the galaxies at redshift 0. Just this video, which shows how the extended disk is being fed from outside. All right, so what do we need to do all this? This work has been done with HST. HST has been instrumental in figuring out all the stuff that I've been showing, but we can do much better, as some of the speakers before me, Fakmi and Chris mentioned. We really want to see, multiple sight lines, and that's possible if we go to much fainter objects, and that's what we need is the successor, a big telescope, and with a spectrograph, that's successor of COS or STIS. The thing is that what we're looking for is everywhere. Faint gas is everywhere. I mean, you could see the covering fraction. The problem is that bright background UV sources are not. And that's what we need to change, is that we need to make telescopes that can look for faint sources, because faint sources are numerous. And if we go to faint sources, we not only limit ourselves to quasars, but we can look for background galaxies where instead of just getting a single pencil beam, we can actually map in absorption and see the size of the structures in absorption for gas clouds that are of the order of 10 power of 14, which would be super, super exciting. The UV is the main regime. I already mentioned that, but I do want to stress this is a beautiful plot from TRIP 2016, which shows that the amount of transitions in the UV is enormous, and this gives us a handle of the physics of the cloud, the ionization state, the kinematics, the different gas structures, even to figure out whether it's an equilibrium or non-equilibrium. All these processes that we can learn from UV is incredible. So UV is the range that we really need to focus, and we need a really large wavelength coverage because we want to cover all of them, because they trace very different types of species, including very cold gas, very hot gas, intermediate species, etc. Anyways, there are other things that we could do. I'm sorry, I lost track of time, so somebody has to shout out for me to stop.
You've got about 30 seconds to a minute left.
Okay, another thing that I want to say that I want to highlight that we could do, which even very good 21 centimeter studies cannot do, is to look for high velocity clouds in distant galaxies. This is one of the famous M61 highly studied galaxies, showing 21 centimeter map, and you can see 21 centimeter, but if you look at with the quasar, you do see the ISM shown in magenta, but also you see high velocity clouds that have metals, that are bringing metals into the disk. And trust me, these are inflowing clouds. And if you have questions, I can explain later. But essentially, the metals that are building the next generation of stars and planets are coming into the galaxies in these very low column density, low mass clouds. We can also see them very easily. All right. I think I do want to stress that there are many other signs. Every spectrum you can take, you can do it for other things, but let's not focus into the details of it. So there's a lot of science that is enabled by these spectra, because they cover everything between us and the quasar, including the galaxy of interest, but in between everything else as well. So I just wanted to take a minute to maybe a little more than what I'm allotted to sort of see what is needed for habitable worlds. So technically, to make a very big revolutionary jump, we need to go to 21st magnitude far UV systems that allows us to look for galaxies as background sources as well as quasar. And we would like to get a signal to noise of 5 and a 1 hour observation. So essentially, for a 3 times the size of HST or 2.5 times the size of HST mirror, what we need to make is our design about 3 times better. So we need to have noise reduction, flux losses, better gratings, better coatings, etc., which we heard about earlier during the conferences, is very, very critical in figuring out how we can get to that number. Again, we need medium to high resolution, and as well as sensitivity across the board from far UV to near UV, so that we get all these species together and we can study what's going on with different high energy and low energy things. The outcome is tremendous, which is basically we will essentially map the gas around it, and it'll have implication of how is the metals injected into the galaxy, or how metal cycling is happening. Where would you find a metal-rich planet, or otherwise? So if we're looking for a terrestrial planet, etc., how far out in the disk you should go to look for a terrestrial metal-rich planet? Those kinds of things can be provided by these studies. Anyways, since I'm out of time, I'll stop here and take questions if any.
Thank you. Okay, so presumably only those who answer the pop question correctly get a chance to make a quiz, take the questions. We've got one question on the floor here and one question online first, please.
Okay, Sanj, it's Fari. Great talk. I wanted to follow up on the NGC 99 example there. I agree that there is co-rotation based on what you showed there, but how do you establish that it's actually part of the same disk as the H1? Because it's so far away.
Yeah, so essentially we have sight lines, including, that goes from the center of the disk, something like this. So we have, so this is just statistical. We have sight lines that go from the disk out to that kind of radii, and you see a co-rotating component always. So essentially that sort of gives me confidence that it's probably part of the same structure.
Okay.
This is Steve McCandless. Very nice talk. I was just curious about the star formation rate in the extended disk around your pole sample.
It's actually quite low. There is one XUV disk galaxy in the sample, but otherwise the extended disk has much lower star formation rate. On an average, it's about 0.1-ish, if you look at 0.1 solar mass per year. And the galaxies have general star formation rate of around 1 solar mass per year.
Okay, thank you very much again, and let's thank all of our speakers in this session. Jason?
You don't have to go home, but you can't stay here. See you in the morning.